Hello and welcome. Today we will be covering the topic of right-angle trigonometry and knowing which of the three trigonometric functions you've been introduced to and where to use them. So right-angle trigonometry is taught using a right triangle. We know that one of the angles is going to be 90 degrees. This angle is usually labeled as a capital C. And these other ones doesn't entirely matter how you label them, but one of them is going to be A, one of them is going to be B. But depending on which one you name B and which one you name A, you need to call the side lengths of the triangle respectively to those names. So the one opposite of B, you're going to actually want to call B, and the one opposite the length, or the angle A, you're going to want to put A. And then the one opposite C, you're going to want to put C. So things that are always true, C is always the hypotenuse. And I mean, that's about all that's always true, although the angles always add up to 180. So say you know A and you want to solve for B. You can either use the trigonometric ratios, or you can quite simply just take 180, subtract A degrees, and then also subtract C degrees. But we already know what C degrees is going to be. It's going to be 90. And then that will equal B degrees. Now, the names for each of the side lengths are going to be the legs of the triangle, except for the longest one, which is the hypotenuse. I don't care if that's spelled correctly. It's probably not. Yeah, okay. Alright, now it's spelled correctly. Now, depending on what angle you look at, these all have slightly different names. Let's say the angle I'm looking at is A. A degrees. Now, the longest side will always be the hypotenuse. That will not change. However, this is not called the leg anymore now that we've narrowed it down to a specific angle. We want to give these their own names. And so, the length here, which is opposite to our angle, we're going to call opposite. Now, there's two ways you can think about which one this is. It's either the only one that isn't the hypotenuse and that isn't opposite to it, or you can think of it as the only angle that's going in a straight line off of your, or the only side length that's going in a straight line off of your angle. The hypotenuse is at an A degree angle going to the side, and the opposite's not even connected to A. So this is the only line connected to A that's going in a straight line. You can think of it that way, but it's harder to imagine that if you've got right triangles that are drawn sideways and stuff, because, well, which one's the straight one? Just think of it as the line connected to A degrees that's not the hypotenuse, or the line connected to B degrees that's not the hypotenuse. And that'll get you the answer. And then it's called adjacent, as it is adjacent to A degrees whilst not being the hypotenuse. Now, how do you calculate any of the trigonometric ratios with this? Well, you might remember them. It is sine, cosine, and tangent. Now, these are all abbreviations that we write for their functions. A function meaning something you write, you put a parenthesis, you have some input, and then it gives you some output. So these are the abbreviations, but if you needed to know the actual names, they are spelt like this. Of course, even then, for cosine, co is an abbreviation for complementary, which I'm not going to write out. However, if we continue to use a degrees as our example, then sine of a degrees is going to be, the opposite length divided by the hypotenuse. Okay? And we like to abbreviate this. Instead of opposite, we write OPP. And over that, we're going to put HYP for hypotenuse. But you can think of this as the entire word if you so choose. Now, the cosine of a degrees is going to be, instead of the opposite divided by the hypotenuse, we're still going to involve the hypotenuse. However, now we're instead going to take the adjacent and divide it by the hypotenuse. So we have the adjacent, and we divide that by the hypotenuse. And then to abbreviate these, if you so wish, you do ADG for adjacent and still HYP for the hypotenuse. Now, what is this tangent thing? We've already done all of these combinations, right? What kind of combination can we make now? We've already used the hypotenuse in every way. There's not going to be something for hypotenuse divided by hypotenuse. That'll always be 1. So instead of involving the hypotenuse, the tangent instead looks at a triangle in a way that doesn't involve the hypotenuse at all. So this is a ratio that is completely independent from the hypotenuse. So tangent of a degrees is going to be, instead of either these, opposite over hypotenuse and adjacent over hypotenuse, it is instead going to be remembered as still opposite on top, like sine. Unlike sine, it's going to be divided by the adjacent. Now, if you were to abbreviate this, this would be OPP over ADG, or J. It is worth noting that this is also the sine of a degrees divided by the cosine of a degrees. And this can be shown because we have opposite over hypotenuse, and then we have adjacent over hypotenuse as this big compound fraction. And when dividing two fractions, we keep the top one the same, multiply, and then flip the bottom one. And so these cancel out, leaving us with tangent. Now, if it wasn't a degrees, and it was instead something like b degrees, we'd still do all the same things. The sine of b degrees is still going to be written as opposite over hypotenuse. However, in this example, the opposites are going to be different from the perspective of where b is. Opposite, instead of being right here, opposite would be this side, adjacent would be this side, and then this would still be the hypotenuse. So you just do the same calculations with that, and that would be your b degrees. The only thing you don't touch from these is c degrees, or angle c. Because this would break our ratios, as the opposite would both be the hypotenuse, and then we wouldn't have an adjacent because there's two sides that could serve as the adjacent, and no way to differentiate between which one to choose. The only things that make some level of sense would be sine of c degrees could be 1 because opposite would be the hypotenuse, but in general you just don't touch c degrees or a 90-degree angle when dealing with right triangles. Later in trigonometry those kind of operations do get defined, but currently with right angles there is no good way of going about those. Now, why is this useful? Let's say I have a tower and I am standing down here, and I know that looking to the top of the tower from where I stand is about a 30-degree angle, and I know I'm about 500 meters away from the tower. Now, if I wanted to know the height of the tower, I'd have to use trigonometry, but how do I know which function, which trigonometric ratio to use in this example? Well, first you need to look at what you're given. So I'm given the distance from where I am to where the bottom of the tower is. That's one of the legs. I'm also given the angle right here from where I am looking up to the top of the tower. So I know that I need to use some function on an angle, and it's going to equal something involving my distance away from the tower. But which one is going to help me with that? Well, from this angle here, we need to realize that 500 meters down here would be the adjacent, as it is not the hypotenuse and is not the one opposite to it. So whatever we end up using, it needs to involve adjacent. Now, we're also trying to solve for the other leg of the triangle, or the opposite from 30 degrees. So we need something that has opposite and that has adjacent. And neither sine nor cosine have both of those, as they have only one of them and then the hypotenuse. So what we need to use is tangent. So we'll take the tangent of our angle here, which is 30 degrees, and then when you look back to our definition, which is opposite over adjacent, the opposite we don't know. The opposite from our angle we don't know. We're going to label that x, or h for height. And so it's opposite over adjacent, but we are given adjacent. It's 500 meters. So now if we want to solve for the height, we need to isolate the variable h. So h is going to be, we're going to multiply by 500 meters, and then that will be multiplied by the tangent of 30. Now the tangent of 30 isn't something you're going to calculate by hand, it's something you're going to put in your calculator. And then whatever this ends up equaling will be the final height of your triangle, or your tower. Now let's say we've got a more complicated example where we have two triangles, and we're given angles up here, not down where we can actually use them more intuitively. To remember about triangles, the angle here, known as the depression angle, is always going to be the same as the angle right in here. And the reason for this is because if you draw a rectangle and then a line straight through the center, whatever angle is here, you're going to have a 90 degree there, you're going to have a 90 degree there. The angle present there, whatever it is, let's say A degrees, and then let's call this B degrees. And then we don't know what these are, but since this triangle splits the rectangle in half, then whatever this is going to be the same as over here. However, it's going to be flipped. So, since it's flipped, B degrees is now going to be over here, and A degrees is now going to be over here. This means we know this is 15 degrees. Now currently, while we can solve for this height and the hypotenuse of this triangle, we can't solve anything to do with the bigger triangle that has these angles here. So how do we deal with that? We want to look up at this tiny triangle and realize this will be a 90-degree angle. And we need to solve for this angle here. Now, solving for this angle is going to require knowing that the sum of all the angles in a triangle should always be 180. We subtract the 90 from the right angle, and then the 5 from this angle. And then this is going to come out to be 85, meaning that this angle up here is 85 degrees. Now, since that's 85 degrees, if we look at the whole triangle, we know that this will be 90 degrees. So we now need to solve for this. Using the same thing where we take 180, and we subtract 90, and we subtract 85, we can now figure out that it should be a 5-degree angle here. You could also realize this triangle here is just a scaled down version of the big triangle, and so the angle here will be the same as this angle here. But you can also work it out as I did, in case you forget. Now we can begin to solve for the height here, and in respect to 5 degrees down here, that should be the opposite. So we need the opposite, and then we're supplied the hypotenuse. So we need something that has the opposite and the hypotenuse, and that would be sine, as that is opposite over hypotenuse. So the sine of 5 degrees is going to be my giant unknown height here. So since I'm already using h as a variable, I'll just use x. And then that's divided by the hypotenuse, which I know is 200 meters, supplied here. So x in its entirety will be 200 times the sine of 5 degrees. Now, we need to solve for this height here. So, in respect to 15 degrees, that would be the opposite. We're also given the adjacent. So we need something that has opposite and adjacent, which would be tangent. So the tangent of 15 degrees equals the opposite, which is going to be, since we call this whole height over here, including h, x, so actually all of this is x. We know that this is, we're trying to currently get the height here, which is x minus h up there. So this is actually x minus h is the opposite, and then my adjacent is 30 meters. This means that x minus h is going to be 30 times the tangent of 15 degrees. Since we know x is this, we can actually substitute that in. Get 200 sine of 5 degrees minus h equals 30 times the tangent of 15 degrees. So now we will subtract this, So we'll have negative h equals 30 tangent 15 degrees minus 200 sine of 5 degrees. And then we need to multiply by negative 1 to get rid of this negative sign. So we'll have, altogether we'll have h is 200 sine of 5 degrees minus 30 tangent of 15 degrees. And then you plug that into your calculator and find out what this height is. Now when it comes to remembering how sine, cosine, and tangent are defined, they're, the most popular way is a acronym SOH-CAH-TOA, which is pretty easily remembered. And what it means is sine opposite hypotenuse, that's what SO is, as sine is the opposite of your angle divided by the hypotenuse of your triangle. And then the CA is cosine adjacent hypotenuse, because cosine is the adjacent from your angle divided by the hypotenuse of your triangle. And then finally is TOA for tangent, opposite adjacent, as tangent is the opposite of your angle divided by the adjacent of your angle. Now this piece is an extra, but if you want to get ahead, then there is sine, cosine, tangent, but there's also three others. There's also three other functions. Now, the co in cosine means complementary, so it's a complementary sign. Now, that's not the only function that gets a complementary. There's also a complementary to the tangent function. It's called cotangent. And if tangent is the opposite over the adjacent, then the cotangent is the adjacent over the opposite. It's also just 1 divided by tangent, so it's the reciprocal of the tangent function. It's really just a special name given to it, even though it really doesn't need the name, because it's just the reciprocal. But that's also what these others are. There's the secant function, and the secant function is the reciprocal of the cosine function, or just, if you want to think of it as the hypotenuse divided by adjacent. And then there is the complementary version of it, cosecant. Now cosecant is 1 over sine, which is the hypotenuse divided by the opposite. This also means something like tangent, which I called sine divided by cosine, can also be written as sine times secant, and that also means that cotangent can be written instead as cosine times cosecant. Now there's a lot of properties for these functions, but the most important that I will highlight comes from thinking away from triangles, instead in terms of circles. If you give an angle, then the sine of that angle will just be the height up to the point where it intersects the circle, and the cosine will be the length to that point. Now the hypotenuse here will just always be 1, so that with your angle, your sine, which is the opposite, divided by the hypotenuse. But since the hypotenuse is 1, then the sine is just the opposite, which is why it's the length there. And the reasoning for cosine is it would be divided by 1, so we'd just ignore the hypotenuse, and then it would just remain the adjacent. Now this definition allows us to think past just, it allows us to even think in terms of 90 degrees, where cosine would then be 0, and sine would be 1. Lets us think of 0 degrees, where cosine would be 1, and sine would be 0. Lets us even think of 270 degrees and other things. Lets you think of any amount of degrees. That's why it's a great definition. But what it also helps us do is realize, using the Pythagorean theorem on this, cosine squared plus sine squared should equal 1 squared because of the Pythagorean theorem. But 1 squared is just 1, meaning the sine squared of any value plus the cosine squared of any other value, but x can also equal y, so they can be the same value, but it will always equal 1. And this also allows sine to be defined in terms of cosine, and for cosine to be defined in terms of sine.